Hi, everyone. Thanks for joining our webinar. We start with the agenda. So we give you a quick overview on the release and then start with solver APIs, C and object-oriented ones before we have Chris talking about the new Python APIs. Then Susanne guides us through the latest Xpress Mosel features, and in particular talking about the Mosel Python API, MoselPy. Then we give you a quick overview of our contributions to open source third-party APIs before we introduce our new VS Code extensions. At the end, we give you an overview of our upcoming Xpress talks, and at the end have time for questions. Please, in the meantime, raise your questions in the Q&A section of Teams. Next slide, please. Okay, just a very quick overview of our release, which went out a week ago. So for Xpress 9.9, it includes algorithmic enhancements leading to performance gains across all our engines, and also includes a new variant of the primal dual hybrid gradient algorithm. This and more will be presented next week by our colleague Timo in a webinar. And if you want to register, you can use the barcode to do this. The solver API side, so the new things there, will be discussed today by Susanne and Chris later this talk. Mosel 6.12 includes the new MoselPy API and further enhancement, and Susanne will explain that to us, how that works. For Xpress Workbench 3.19, there are only minor feature enhancements. Most important of all, the macOS Intel platform, like same for Solver, is not supported anymore. And macOS ARM will now be the only supported platform. And also, we remove our IDE installer from the installation package, but we build out our VS Code extensions, which we will explain later. Some announcements to make, and my colleague Chris will give more details on how to do that later. Since many of our customers prefer nowadays PyPy over Anaconda for Python package management, and also it requires a commercial or paid license for bigger companies, we decided that FICO optimization products will transition away from Anaconda as an underlying package manager. So with Xpress 9.9, also Insight, which is affected 5.17.2, that will be the last release to be published on Anaconda. So subsequent new releases will be published on PyPy only. But as said, Chris gives us some more details on that. That was the intro. I hand over now to Susanne to talk about the solver APIs.
Well, welcome everybody to today's talk. This portion about, can we perhaps switch to the next page? It's going to be a sneak preview of the talk that my colleague Timo Berthold will be giving next week. Just a very rough overview of features that are also mirroring through to the new functionality that is also present in the different other APIs. So we have a new function in the C API, a trigger restart to restart the MIP search that can be called at various places, including callbacks. Next, please, Chris. And then we have a couple of new controls. Most importantly, and that's very visible also at certain interfaces, and we have deprecated the little L flag for Xpress Optimize and Xpress MIP Optimize, which was so far enabling you to stop a MIP search after the initial LP solving, so after the initial relaxation. Instead, now actually we are introducing a new mechanism that is called MIP stop stage, which is a control that has different values. And this allows you to stop not just after the initial relaxation, which is one of the possible places, and this would result in exactly the same behavior as the previous stop, but also after the pre-solve, after the pre-root heuristics, and also after the root, so after the heuristics that have been cuts and heuristics from the root node. So what you do now, instead of setting this flag for the optimization commands, you would set MIP stop stage to initial relaxation, start your optimization one, and then set MIP stop stage to none, and continue your optimization one. So second call to your optimization command just as before. And of course, this behavior echoes all then to the different interfaces. Other new controls, so you're going to hear more about this next week. Max total tree file size to limit the data size that is written in a single solve to your disk. Well, a setting for the background threads, and also a new control relating to the use of GPUs. Next, please. So as I mentioned, this is just available on all interfaces. Now, object-oriented interfaces. Well, a couple of minor updates really. So it is completing the overloaded versions, completing the behavior. So we have a couple of new member functions, mainly overloaded versions of existing ones for mainly handling of nonlinear expressions, so more convenient ways of specifying nonlinear expressions. We have also worked on the exception handling to improve the behavior for certain error situations. And we have improved the reference documentation for callbacks that has been flagged up as well being insufficient. Okay, next please. And then specific changes, always having in view a as similar look and feel as possible between the different interfaces without sacrificing really the language specifics. So we have renamed a couple of routines that relate to sensitivity analysis. Yeah, and with this one, I would like to hand over to the Xpress Python API, which will be presented by Chris Brown.
Thanks, Suzanne. So just a quick overview first. I'm going to start by talking about changes to platform support, Python supported versions and pandas versions, then move on to cover the new features in Xpress 9.9 relating to Python, along with some more minor changes that are included in this release too. So first of all, as Alex mentioned, Xpress 9.9 will be the last release that we publish to Anaconda. Subsequent releases will be published to PyPy only. So whereas in the past we've made Xpress available basically in two different formats, going forwards it will only be available in one format. But this really, I just wanted to clarify that we do still support the Anaconda environment. So if you use Anaconda in your organization, and that's how you structure your projects, Xpress will continue to support these Anaconda environments. It's just that the package will come from PyPy instead of from the Anaconda channels. Those of you who use Anaconda will know that there are a few different channels where packages can be made available. There is the Anaconda main channel, which is the packages that are officially provided by Anaconda. And then there is also the Conda Forge channel, which is provided by an open source organization. So for example, when you install NumPy, you often have a choice about whether you want that to come from the main channel or if you want it to come from the Conda Forge channel. And the reason that I mention this is that primarily we will support Xpress in conjunction with packages from Conda Forge. So for example, Xpress relies on NumPy as a kind of required dependency, and we will be testing and supporting the versions of NumPy that are shipped on Conda Forge. The existing packages of Xpress that are already available on Anaconda will continue to be available until those releases go out of support. So in particular, the 9.9 packages will be there for the next 2 years at least. But yeah, releases after 9.9 will be publishing only to PyPy. So if you do use Anaconda and you want to continue using Anaconda, then our recommendation is just to use pip to install Xpress into your Conda environment. You can install NumPy and other dependencies from Conda as before, and then just install Xpress from pip. Also, if you use an environment YAML file to configure your Conda environment, you can specify the Xpress as a pip package as shown on the slide. So moving on to supported Python versions and Pandas versions. So firstly, we've added support for Python 3.14, which was released in the last few months. And we've also added support for Pandas 3. Python 3.9 is now out of support, so that's been removed from Xpress in that 9.9 doesn't ship any 3.9 packages. And we continue to support the Python versions in between, that's 3.10, 3.11, 3.12, and 3.13. And we continue to support Pandas 2 as well, all the different flavors of Pandas 2, since they are also still supported. Okay, so now I'd like to talk about a beta feature in Xpress Python. You might have heard about the new free threaded builds that are available for Python 3.14 and 3.14, 3.13 and 3.14. So I'm going to give a quick overview of those new features and then talk about how they're supported in Xpress. So historically, the standard CPython interpreter that most people uses only allows one thread to execute Python code at any one time. You can have multiple Python threads, but they will wait for each other essentially. And this mechanism, the mechanism that kind of makes these threads coordinate with each other, is called the global interpreter lock. Only one thread can hold that lock at any one time. But since Python 3.13, free-threaded interpreter is available. And this free-threaded interpreter allows multiple Python threads to run concurrently. So you can parallelize your Python program, have multiple Python threads working on different tasks at the same time, and they don't have to take turns anymore. This free-threaded interpreter is a separate installation of Python. It is a separate version of the interpreter. So when you install Python 3.14, for example, you choose whether you want the single-threaded or the free-threaded version. And the packages that you install have to be compatible with one or other of those versions. So the beta support in Xpress 9.9, as part of that, we provide partial support for free-threaded Python 3.14. So that means that on PyPy, there are packages available for single-threaded Python 3.14, but also free-threaded Python 3.14. And depending on which version of the 3.14 interpreter you have installed, when you use pip to install Xpress, it will download and install the correct one. So the limitation in this beta is that the Python interface itself is still single-threaded. That is the Xpress Python interface. And by default, in order to preserve thread safety, if Xpress is loaded, it will force the interpreter to run in a single-threaded mode. It is possible to override that using the xgil command line option that you can see on the slide there. So this could be useful if, for example, you want to experiment with using threading in other parts of your program that aren't related to Xpress, for example, processing data before building your model or processing the results of optimization. All of that kind of thing could be multi-threaded. If you do make that choice and you want to take responsibility for thread safety yourself, then you must make sure that you only use the Xpress interface from one thread, firstly. And if you're using callbacks at all, then you must set the callback from main thread control to 1. And what this control does is it makes sure if the optimizer calls back into your Python code during the solve, all of those calls will only occur on the main thread. So that ensures that you never have multiple threads kind of interacting with Xpress from the Python side. And that's necessary because, of course, the optimizer itself is multi-threaded and supports a high degree of concurrency. It's really just the Python interface that kind of requires this single-threaded functionality for the time being. When the feature goes out of beta status, we expect to support a much more comprehensive and concurrent programming model. Next, just to talk about an update to the linked API. If you've attended any of our previous webinars, then you would have heard a lot about the new Python linked API that we introduced in Xpress 9.4. We call it the linked API to distinguish it from the older legacy API, because in the new API, variables and constraints have to be linked to a single problem. In older releases of Xpress, variables and constraints could belong to several problems, which led to some limitations in the API, along with confusion at times. For example, if you modify a variable, which problem are you really modifying if that variable belongs to more than one problem? The last release, Xpress 9.8, introduced a more consistent set of functions on the problem object, following a signature convention and a naming convention that's more logical and also more consistent with our other APIs, such as Java, C# and C++. The main differences from the legacy API are that the new functions use this camel case naming convention that you can see on the slide, as well as always returning their results using true return values, while in the legacy API, we'd often use output parameters to return values, which was sometimes a source of confusion. In 9.9, the changes are to extend this new convention to the Xpress module objects, such as express.getVersion and other kind of global functions, and also to the branching objects API. The branching objects API is one that you might not use often, but if you were to implement a custom branching algorithm during Express MIP search, then that's the API that we'd use for that. This is planned to be the last release that makes significant changes and deprecations to the Xpress API. If you haven't yet looked at migrating your Python code to the new API, there is a migration guide that you can find referenced on the slide there. That guide talks you through how to transition from each of the older functions and older styles of creating variables, creating constraints, and calling functions on the problem, how to migrate to the new style. All of the legacy functions that have been replaced by new signatures are deprecated. They will produce warnings at runtime. And to suppress those warnings, you can use the code that you see there on the slide. In addition, there's a full list of deprecated functions in the documentation, and the documentation mentions which function you should use instead if you're calling a deprecated function, for example. Okay, onto a feature that's been requested by several customers, which is an easier way of naming constraints when you're adding them to the problem. So previously, to name a constraint from the Python interface, you'd first have to create it and then assign the name property, or you'd have to use this explicit name constructor that we have that takes a name argument. And this is a little bit clunky, not the most Pythonic way of doing things. So in Xpress 9.9, the problem.addConstraint function now has a name argument. As you can see in the first example, that allows you to specify a name when adding just one constraint. But also if you're adding multiple constraints, you can specify a name prefix. This is very similar to what we have when you're adding variables, and a suffix will be automatically generated for those constraints. The object that you pass containing your constraints could not just be a list, but it could also, for example, be a dictionary, in which case the name suffixes are derived from the keys of the dictionary. And they can also be multi-dimensional arrays, in which case these zeros would become 0, 0, things like that. So it's very similar to the functionality that we have for variables. And then the final pattern that might be useful is where you can specify not only an array of constraints, but an array of names for each one. And this pattern is particularly useful if, for example, you're using pandas data frames to create your model. Then you might have the expressions or right-hand sides for your constraints in series of the data frames, and you might have the name in another series, in which case you can just pass it directly into the add constraint function and pick up the name from there. Okay, now I'd like to talk about some changes in behavior relating to accessing the properties of objects like variables and constraints while in a callback. In a multi-threaded solve, several callbacks could be accessing the same variable, and this could lead to some potential issues. In particular, accessing a property of a variable from a callback, like its upper bound, sometimes raised an error and sometimes succeeded, and that would depend on whether the callback was running on the main optimizer thread. We've now made this behavior more consistent. Primarily, all property access, variable and constraint properties, this is forbidden in callbacks going forward, so that will always raise an error, because it just isn't possible for us to consistently provide access to that data from the underlying optimizer. There is one exception, which is the name property. In the previous release 9.8, because of these difficulties accessing the data, the name properties were assigned placeholder names such as C0, C1, C2 for columns variables. But in 9.9, the names are actually now available. So you can access bar.name, constraint.name, things like that from callbacks, and that's not a problem. And the reason we've done that with names is that it's very convenient. For example, if you're adding cuts in a callback, you want to print out your cut expression, having the variable names there in that expression makes it a lot easier to debug your program. Yeah, so for other data, besides the name, such as bounds, right-hand sides, that kind of thing, you'll need to make a copy of that data in a local array, for example, before you start the solve, if you want to access it from a callback. Similarly, functions for accessing the solution are no longer available. We did introduce functions to access the callback solution, which, while you're in a callback, returns solution values that kind of relevant to the current callback. For example, in a MIP search, in the callback that's fired when a new node is solved, that callback solution function will return the LP relaxation solution for that node, rather than the overall incumbent MIP solution. And because of the thread safety issues, these functions are no longer available, but there is a simple replacement, which is to access that data via the callback problem that's passed into your callback function. So for example, if previously you would have called variable.getCallbackSolution, now you would call problem.getCallbackSolution and pass the variable in as an argument. So finally, I'd just like to mention a new feature in the optimizer. Look at how that's exposed in the Python API. This particularly is for multi-objective problems, where we solve for multiple different goals, the same problem. It's now possible in the optimizer across all the APIs to set different control values per objective. That means, for example, that you could have different tolerances, depending on which objective you're solving, different time limits, different resource limits of other kinds, even different strategies when it comes to the algorithms like heuristics and things like that. And these are exposed in Python using a new property on the problem called OBJControls. This is a kind of list-like problem. It has an entry for each objective in the problem. And each of those entries exposes an object that behaves like problem.controls, in that you can assign control values to it. So this example shows how to set a distinct time limit for each objective. Yeah, and that is basically all I was going to cover for Python. And I think now we are jumping back to the VS Code demonstration, or are we moving on to Mosel?
Whichever works better for you, Alex. Are you set to start the demo?
Maybe you continue with Mosel now.
Okay, then yeah, I will take this screen and share. So if you stop sharing, Chris, then I can take this screen. Okay. Yes, so what we have got for this new release, we have a number of performance enhancements for specific operations. Well, I'm going to go through these things in detail afterwards. We have, as a larger new feature, the new Python API for Mosel called MoselPy, which is coming out now as a beta release and will be the final, or is planned to be in the final stage for the next release of Xpress. And then, well, a couple of smaller features. But let me go through these things in detail, starting really with the major piece. So MoselPy. MoselPy is a new Python package that we have created. Well, this will be available as a download via PyPI, so pip install. Given that we are moving away from Anaconda, this is not going to be on Anaconda at all. In this present version, it will be supported for Python 3.10 through 3.14, just like the other packages for Xpress. Well, the functionality is what you usually expect of APIs from Mosel. So what we have for Java, for .NET, also VB. So you have the model handling. You have post-processing interface functions to access, to retrieve information from models. So this is one way. The model runs and you retrieve information. And then we have the I/O driver, MoselPy, for exchanging data in memory between Python and Mosel. And this is two ways. So I have data in Python, sending it over to Mosel, and then Mosel getting back data, result data usually, into the Python program that serves as host to the Mosel model. And this interface also supports Mosel's binary data format. In this beta version, it is not meant to be used jointly with Python 3, which is really reasoning the other way around. So there is Mosel calling out to Python, so Mosel in control of the entire process, whereas MoselPy, Python is the host program, and you have Mosel then running within Python. So either or. As I said, you install this via pip install. The MoselPy package will be available for download within the next couple of days. And well, for this initial version might also require an Xpress installation. And well, you can of course then also use this within notebooks, but we are planning to have a separate session on this and really walking you through examples, in particular for notebooks. So first of all, just the basic concepts. As I said, model handling. So the standard sequence of working with Mosel models is compile, node, run. You can, well, compile, you have the Mosel model that needs to be transformed from a text format to the BIM, so the binary model format. You can skip this step. I mean, you can prefer your BIM file offline and work just with the BIM file, the binary model version in your Python program. Well, there are a couple of advantages to this. So you have your model source. It can be included with Python, but it can be also kept completely separate. So you can work with your Mosel model offline, develop it, debug it, completely disconnected from whatever environment you embed it into. It's not specific to Python. That's applicable to any of the Mosel APIs. Really having the model detached so that you can work on this as a team and you have different components that are clearly separated and can be looked up separately. Now, for Python also, what is of interest is actually if you work just with the binary model, well, that's a binary format. It is a proprietary format. It is not encrypted, but it's binary, so it is actually protecting your IP. Whereas if you have a standard model as a Python program usually, well, this is by and large visible what your mathematical model is doing. Okay, so now we have our binary model. We need to load it, and then we run it. And at this one point, we instantiate the model with a specific data instance. And then, of course, we can retrieve the data or results from it. Of course, we need to check that it has run correctly and provides results. This compile root run sequence can also be aggregated in a single execute step. Well, either execute model providing a MOS file, then it's, or we can provide a Vim file and then it just uses the Vim. And by freeing resources, you can reset it so that any result data, anything that has been generated by running the model gets freed up without unloading the complete Mosel environment, or with the Python. So it's the explicit reset, or you use this with Python's context manager, and well, you have this as a with expression. Okay, now how to feed data, how to instantiate the specific Mosel model. As always, you have runtime parameters. So limit would be something. So this label here is something that is declared as a runtime parameter in Mosel, and you provide values to this. So these are scalars that appear in the parameters block at the beginning of your Mosel model. For retrieving information, you have MP with our Mosel Pi environment that we have loaded, and you can have the version, the Mosel version, and Express version out of it. Now, what does this look like? We have here our Mosel Pi. We compile node 1, and here we are using the post-processing interface, meaning run our model, and then afterwards we interrogate it. What have you got? We can only ask for something that has been marked explicitly as public in the Mosel model. Otherwise, the information is not reachable, at least not with default compilation, from outside the Mosel model, because the model protects whatever is its contents unless something has been marked up explicitly as being public. Okay, so here the idea is I have something that is called sol take in my model, and I have got something that is called value. Well, spelling, of course, Mosel is case sensitive, so it needs to be spelled exactly this way. I'm finding these things, and well, then I can iterate through this, assuming this was a solution value and the other one was data, and then we can just print it out in our Python model, in our Python program. Here, so the Mosel arrays are retrieved into Python dictionaries. This is the corresponding Mosel. Sorry, this was not the Mosel model from the previous page. The previous page really was just a standard Mosel model with some public markers where we retrieve data. Now we have the second type of data exchange using the I/O driver. So most often a Mosel model, if you run it standalone, it takes data from a text file, a database, some Excel spreadsheets, perhaps also writes it back. So with this, we use the initializations from and to mechanism of Mosel. So default configuration here for the model would be, I just use a text file, and then I read my data and perhaps also write it back after the solution is run. Now we just take this model source here and well, have it fed with some, so we're overwriting these execution parameters. So the data source is no longer a text file, but we say take it from Mosel Pi. So take it from Python memory, because we actually have the input data here, and we would like Mosel to write it back. So what we have here is we provide exactly using the labels. So input data is a fixed label also, it's predefined, and within we provide a collection of from lists, the labels, and then the actual data. So labels always matching what is used in the Mosel model. And what we have here also then for retrieving output, again, highlighted here in light blue, output is another predefined marker, and within I can now reach the, again, the label used in Mosel for an entity. Now with this case, because this was, I'm scrolling back one page, here there was no particular public markup, because I have the initializations from two sections that decide what data is going to be read and what the Mosel model writes back. So there was no particular other markup, just like standard data exchange from Mosel. Okay, just a couple of notes here. So how we match up types. For the basic types, I mean, that's kind of obvious. Arrays are dictionaries in Python. When we have Python list tuples or sets are mapped to sets or lists, depending on how this is declared in Mosel. Well, bytes, I mean, this is the raw data for the binary data, binary driver. I'm coming to this in a second. Panda series matching to arrays, but in a slightly different way. So the index becomes the array key, and the name is used as an identifier, as an identifier if it is not specified. Then we have the data frame. So that is really a two-dimensional table and represented as a Mosel array. First index, integers, row counters. Second index, moving across, if you think about this represented, so two-dimensionally. So the columns, these are by using the field names. So that is usually a text field, so a string index, the second one. And then we have the NumPy ND array, which also matches the Mosel array. Okay, so that was the type correspondence, which just happens automatically, as you have seen in the previous examples. Then we have done a couple of other things. If you're running a Mosel model embedded in host application, you want to be able to retrieve your output stream or your error streams, or could also decide to ignore these streams. Certainly, at least for the error stream, really not a good idea, but it is, as it is shown here, it is possible, for instance, to just simply disable the output by redirecting it onto the null stream of Mosel. And by using none as the file name to restore Mosel's default behavior. Okay, so the redirection can happen either per Mosel model. So what I'm loading is one Mosel model, or I can put this on the Mosel instance, but any setting needs to be made before I do anything else. So before I load any models into it, and then it applies to everything unless I make per model settings, which will take precedence over the general ones. So now here, this is the implementation of binary format. So we have a two-binary transformation of Python data. Yes, so there's a scanner and an array contained in this collection. And here now we are specifying. So previously there were predefined labels that we are working with. And here now I'm specifying a new label. I'm saying, well, that's going to be this bin data that I've created. And how I use this from Mosel is, well, I'm using MoselPy with this light blue label where to take things from. And it has been binary encoded. Well, binary encoded data is smaller for exchange in memory, or if I want to send this, for instance, over the network to some other machine. So it is, it is smaller in its representation, and it guarantees full precision for floating point numbers. Well, and then I just use my labels that need to correspond again to what I've used within my collection. Well, I can use this labels also on MoselPy, for instance, also for other purposes. For instance, if I want to include the Mosel model as a source into my Python program. Well, why would I want to do this? Well, you can imagine situations where portions of the Mosel model are generated by the API. So you don't have a fixed, complete Mosel model text existing in a separate file, but actually it could be generated dynamically. And there you have then the model sitting within your Python program. And so I can compile this from memory into, well, here it is just straight away executing the model. Okay, so that was the functioning of the Python API. So not much different from what other, in particular Java API of Mosel is doing, but of course you have these specifics, for instance, data types, in particular data frames that are specific to Python. Okay, now coming to other features that we have for Mosel, performance enhancements. We have the array assignment. Well, if we have two arrays, but here I have A and B with anonymous indexing sets, so they are not named. So I can just assign B to A, and I have, well, equality here. So that's evaluating to true. That's not new. This has always been like this. What we have now is actually, we have two sets, and they have different names for the indexing sets. All the rest is actually, when they are same type, same number of dimensions, but they have different names to their indexing sets, and they actually contain different things. So this previously was going wrong. It is now possible. So simply to assign what A has in contents, I am assigning B to it. And so with this one, I'm overwriting A with the contents of B. Now, both of them are actually in the, let's say, they are fixed. So they are not standard arrays, so not with dynamic markers or anything. So actually, by assigning these new indices, and because they are ranges, I'm actually completing the index set. So the new values for A is going to be 3, 4, and then up to 7, 8, because these were already in its index set, but I'm overwriting. So I only have the values 1 and 3, so these indices 3 and 4 defined. And because A already had some entries, it is bigger actually as B. So bigger than B. So here the equation evaluates to false. If I now make a dynamic, this will behave as expected. So the override is complete. I'm forgetting completely about the previous indices that were in A. And here now the equality comparison evaluates to true, independent of whether B was dynamic or not. Okay. Now this array assignment, comparing A1 assigning B, or the individual copying over of entries, even for very sparse arrays, or in particular for very sparse arrays. So here I'm operating with a density of 0.05% only. And here just the corresponding, just the tests of this loop. So of course but doing this copying as one operation as opposed to running through this sparse, although this XS test is a very efficient way of enumerating loops in Mosel, but it is simply more efficient because I'm copying a huge chunk of memory as one, and I don't have the individual assignments. I have another enhancement here. This is the set intersection operator. Well, you can have manual intersections written like this, or you use the intersection operator. So this is for an intersection between several sets at a time. So here, this is for a test case turned out to be about 3 times faster than the for a specific test case. But for MMNL, so the handling of nonlinear terms, here we have worked on the efficiency for matrix generation for large numbers of variables on linear constraints, and there again we have performance improvements. This now is the feature for MMXPS. So as I said, across all interfaces, but here just the example for Mosel. Previously, if you had minimized, LP stop, and perhaps do some heuristics, load solution or something else where you wanted to interact, and then continue. Now you replace this by surrounding the initial call with MIP stop stage, first the initial relaxation, and then removing this stop, and this cont piece, so to continue this solve, remains as is. And yeah, so we have the different values that we have seen, so more possibilities of interaction with the Xpress solver. And if now I was halted by the stop stage, so there's a new value also for the stop status. So if I have this initial stop, then I actually can see this as the stop stage value. While at it, we have added a couple of other constants. So here for the objective sense definition, this was previously just numbers. We have also worked on a couple of other specific cases, in particular handling of quadratic expressions. So here, actually a lower memory consumption. If we detect quadratic objectives or constraints as opposed to just handling them as general nonlinear expressions. For MMJobs, there is a feature that was requested by users. Already existing was actually the way of writing shared memory and deleting all shared memory. So shmem : asterisk, which removes all shared memory. We have now a way also getF size to report the amount of memory used by shared memory. We have been asked also to provide more fine-grained details on or reports on shared memory blocks. But we have actually decided not to provide this functionality because while shared memory is not just written by a single model, but actually a model can access all shared memory that is shared by the Mosel instance. And there we have the idea that we want to protect data. So if we could make everything that lives within the Mosel instance in terms of shared memory visible to a model, but we would work against the standard protection mechanisms of Mosel. So we report now on the file size. So perhaps you've forgotten to free something and it just goes on living a big block in shared memory. So now you can at least detect this, either generally with the asterisk or, which already was possible previously, you can use the name of a specific label and see how big is this block of memory that I have saved in Mosel memory. Okay, QSort has got a new version so that it can actually now be used also for lists or lists of sets or list of lists with a comparison routine. So specifying how to sort a list. So here I have a list of lists and I say, well, I want to sort them in ascending order. And my comparison function defines how to compare these lists. So actually first I'm ordering them actually by size and then within a list of the same size by entries. For the Java, we have deprecated the finalized methods and you now you use the close operators, so standard Java instead. Makeutil has a new parameter to do. The to do existed, but now it can actually take a list of targets and not just one target. There's also a new subroutine cmd sub-st to retrieve the output of some system command into a Mosel text. S3 now has a more detailed handling of HTTP status calls and also including Amazon error calls, so on AWS. Mosel doc handles now the image tag, so you can have markup that includes an image, and then it is expected to find this image file in a subdirectory called graphic to produce a nice document partition going along with your Mosel model. The updates are in the Mosel language reference manual. We have a separate manual for S3 and Java, and there is a new guide for the Python Mosel PyAPI. This also comes with a new chapter in the Mosel user guide, and the corresponding examples that are discussed in the user guide are under examples Mosel user guide C2. A general remark, not just linking to or related to Mosel, is that the new Xpress distribution includes markdown versions of all Xpress solver and the Mosel guides. We have found that if you wish to use the Xpress documentation with LLMs for searching our documentation, it is more efficient to start off with the markdown format as opposed to by the provided PDF versions. So now you get immediately the markdown format output. Well, any questions at this point? Where we switch over to the other presentation to move on, to go on with the APIs. First the VS Code extensions, if you want, Alex.
Yeah. Okay. Thanks, Susanne. Yes, I give you a quick overview of our motivation for VS Code. So, I mean, we know it's a preferred IDE by many, and it was also requested many times by you, our customers. So we are happy to provide support for Mosel and the solver for our tools. We start with 2 extensions for now as a beta, and the full version will follow. So we have the Mosel extension, which supports modeling and optimization with FICO Xpress Mosel, basically providing language support and Mosel runtime. And we have a solver extension, which supports, for now, primarily tuning with FICO Xpress. Before you get started, for most of you may be familiar, you need to have installation of Xpress. If not yet, you can check our community license and download the installer from there. Downloading the distribution also gives you access to many examples and documentation, as Susan mentioned, for instance, if you want to use it with Markdown files. Then you need to install VS Code for your operating system. And once this is installed, go to search in the marketplace FICO Xpress, or then you will find the Mosel and the solver extension. Each extension has a README with a lot of useful information on features and how to use it. And we will also publish some blogs in the next weeks to ease your migration to VS Code. Okay. So I hope you can see my VS Code now. So this is basically the Mosel extension, which is installed from the marketplace. As at the beginning, we have a long list of features which are documented here, and you can try. So code folding, jump to definition, code completion, and so on and so forth. So a lot of stuff what you expect from a modern IDE. I quickly want to demonstrate some features from the runtime and debugging at an example of an Mosel file here. This is from an Inside app. And on the top and right side, you can choose debugging, running, or compiling a file, right? So if you start debugging, the debugging panel appears and you can step through the code, right? I mean, you can hover over certain information. It appears in a variable section. And for instance, if you want to have more detailed information, you can have a variable inspection view, for instance, for the result file, which then appears here. One thing to consider is that you need to update with every iteration, right? But then you have the flexibility to either export it or sort this file. And basically, this is the functionality we provide for debugging. There are other options to run a file, right? You can use the command palette for that and type Mosel, for instance, and then you see all the functionality, but you can also create custom tasks. So for instance, like I did here, which you need to create in the VS Code folder. And here, for instance, I created a task, a debug task. I call it my task debug. The only difference to the other one is that it creates an output BIM file in my source folder. And if I want to run this, I need to push run task, and then I run this task, and it runs the same way, starts the debugging, but stores the BIM file in a separate folder. So this is just one example how you can customize tasks and ease your life around that. The other function we have is our tuner. Just showing here again, you can download it from the marketplace, and you have some documentation there which helps you how to use it. I think the idea is, as many of you know, I mean, the default Xpress solver settings work really well across a broad range of problems. But if you want to solve one problem more intensively in production, it has a good and important impact to do some tuning. Our motivation was that this capability has always been with the solver, but maybe not accessible to a broader audience. So it was more appealing for the advanced users. So with this new extension, we think the functionality gets more accessible because it has got a very nice UI for that. And how do we do that? We support matrix file, MP, MPS format. And here you have one of those. And then you can basically hit this dialog button and you can choose a simple solve or a tune. And for the tuning, you can configure parameters like limit the time of the solve to 1 second. You can choose the tuner method and so on and so forth. And then you can hit tune and it runs, and our results are then in such a nice table, which you can also sort according, I don't know, objectives or the runtime. And if you pick a version you want to work on, you can also get the control parameters in Mosel, Python, or generic ones and copy them to your code. Yes. As said, we will provide more instructions and blogs about this that you can easier adapt to that process. But I think considering time, I want to move on to the end of this presentation. Suzanne, are we gonna have a quick summary of the open source APIs before we wrap it up?
Yes, just very shortly. So here we, well, this is what we usually have. I mean, this is what we've been talking about. We have the C as the base implementation for the solver and various object-oriented and also the Python API on top of this. Next page, please. And so this is what we're distributing with the Xpress stack. Now what we have is actually, well, a couple of other interfaces. Some of them were written originally by external people, but some of them have been newly created. If you please go on to the next page. So these are external third-party interfaces that are published open source. And what we've done, well, last year we published a new Julia interface. Now we also have Jump. We have implemented a new ORTools interface for Xpress. There is a PyOpt interface, which is Python, but it is based on C++. And then there's a host of other Python interfaces that are based on the Python API. And for AMPL, we have, for the Xpress connector there, we have completed and helped updating the documentation. Next, please. So everything, I mean, I've also put the link into the, put it into the Q&A. I hope this is visible to everybody. Otherwise, just follow this link here to see the FICO GitHub repository. And there you see a list with pointers to the different external APIs in case you're interested in any of them. Okay, next page, please. Yeah, there's also a blog series about how to use these different interfaces. So of course, they are not doing all the same. Not all of them, for instance, support nonlinear expressions. Not all of them even quadratic programming. And so, well, there is a host of different combinations of functionality for the different interfaces, but you could choose, if you wish to use one of them, you can choose, of course, what fits your need. Well, with this, back to Alex for the closing remarks.